chord. Sorry about that. Close. We're almost there. Gives you a few minutes to digest what I just said. So wherever I get 3 dB below that peak value, whatever it is, that is my 3 dB frequency. A term you hear a lot out in the real world. And this value down here, the omega value of that should be my omega naught. This is like the most common response that you will see out in the real world are these low pass filters, not some of the stuff that I gave you to make you stretch your Bode plot brain so you don't freak out when you see what the transistor frequency response curves look like in 380. They're really messy, but what we do is we put a pole in there so that we don't care about the messy part. And then they look like low pass filters again. Okay, I modified this to give you some real numbers. Kiloradians per second, which is about 2 kilohertz. Most people in industry talk in kilohertz, not kiloradians per second. Mathematicians and signal processing people tend to talk in radians per second. And the difference between the two of them is just omega equals 2 pi f. And f is in hertz or kilohertz or megahertz. And omega is in radians per second. Okay. So we've already figured out these equations. We go to Cedra Smith, which is your textbook for this class after the exam. We'll use it in 380 and just keep it for a reference book. What I want here, we looked up, you could derive them again, or you could look them up. The DC gain is R2 over R1. And I want to start out trying to do this with an R1 of 1K. A lot of times you get to pick your first value. But the spec says I want a DC gain of 1, and I want my cutoff frequency to be 15 kiloradians per second, which is about 3 kilohertz. So I go through and I calculate. I've got R2 over R1 has to equal 1. So that means that R2 will also equal 1 k ohm. And my omega naught's 1 over R2C. So I'm given, I have R2. I can plug that value in. It's 1K. I can get C is 1 over the omega naught over R2 and calculate that, and it comes out to be 66.7 nanofarads. A lot of times when I'm actually doing that and doing this and I'm picking values, I pick the capacitor value first because I'm limited in my choices of capacitor values. I put it at microfarads or nanofarads or something like that. I calculate the resistor values, and in general, I want my resistor values to be K ohms, tens of K ohms, maybe hundreds of K ohms. And I want my capacitors to be somewhere between maybe microfarads, nanofarads, or picofarads. And as long as I'm kind of like in that and in that range, I'm okay. So that's how you design a filter, and it's fairly easy. And these are reliable, they're cheap. I can get gain and frequency response in one circuit, and they're better than the RC filters you'll see in the lab. If I want a high pass filter, okay, this, all I've done here, I've taken this circuit, look, this one has a C in the feedback loop. I've moved the C. I put it in the input network. I go through, and now it's in series. I can go through and do the same math. My feedback resistor, oh great, just go away. My feedback resistor is now R2. My input resistance is the series combination of R1 and 1 over SC. So I divide those two, and I get this. This is ZF over ZS. Did somebody chat at me, or is that the old one? Oh, this is a new. You're right. This is a new one. Somebody's chatting. Yes, it is. It's the worst virus on this computer, and I can't figure out how to remove it. I tried once, and then I just said, okay, I'll just unclick it. Okay, so we've got this. Again, it's a messy fraction. So I'm going to multiply by SC over SC to get rid of that. I get SC R2 1 over 1 plus SR1 C. Okay. So this looks like some gain times, now I have a 0 at the origin. And this is about the level of what I make you plot on the, maybe on the exam. And this is a pole at omega C. The DC gain is R2 over R1. That minus sign just becomes a pesky 180-degree phase shift. We'll talk about that later. Why 180-degree phase shift is really bad. And omega C is at 1 over R1C. When you get the high-pass filter in lab, the first week of lab 4, these are going to be real values here. These are going to be like kiloradians or megaradians per second, where this cutoff is. What you're doing, let's see if I can explain this. I'll probably have to explain this again in the lab. You've got a Bode plot that looks like this. You've got some K value. You have a, let's do the pole first. You have a pole, this is K. Your pole looks like 0 dB until you get to omega naught, and then it starts to fall. And then you've got this other pesky term back here. And let's say this is, you know, your graph is going from 1 megahertz or megaradians per second, 10 megahertz, 100 megahertz, something like that. You've got a 0 at the origin, and the only thing you know about the 0 at the origin is the slope is positive 20 dB per decade, and it passes through the 0 at the origin. Let me write this down. Passes through 0 dB at omega equal 1. And omega equals 1 isn't even on your graph. I've seen people try to like draw the graph out to omega equals 1 and have this really huge graph, and that's not the thing to do. One thing that's interesting about this function here, if I plug in, I got h of s is equals this. There's this little trick here. If I make h of j omega c, wherever that pole cutoff frequency happens, magic happens. I get k j omega c over 1 plus S is j omega over j omega, so this becomes, I think it's j1, something like that. Okay. If you plug in the values at omega c, what you get is 3 dB. It's the minus 3 dB frequency. So the way these high pass filters work is you don't plot the components because you can't do that 0. You just plug in omega c, you get minus 3 dB, you know that's your cutoff frequency. It's going to be flat after that. it's going to be positive 20 dB per decade going up to it. It's a shortcut to avoid having to plot that third thing that you can't plot on that graph. I've seen all kinds of crazy ways of people making the math really hard on that. The easiest thing is just say, okay, what's going on at omega C, and know the shape of the curves. And this will be whatever K is, 20 log of K. Okay, I will be in the lab when that happens. So in this case, I picked my C, and different capacitors have different, some of them get, it's same value of capacitor, but some manufacturers prefer to label them in nanofarads and some in puff. 0.1 nanofarads is the same thing as 100 puff. So I've got a C value. I've gone through the math and I figured out what omega C is. It's 1 over R1C, and I want that to be 500 kiloradians per second. So now we're up in the AM band. And then you can calculate R1, and R1 comes out to be 20 K ohms, because you know C. K is R2 over R1. You've just calculated R1. You want that to be 20 dB. Ooh, how do you do that? I see people have trouble with this too. dB, dB volts is 20 log of your gain. Okay. What if I know the dB and I want to solve for the gain? I have to divide by 20. And that equals the log of AV. And this is where you start sweating because you don't remember Algebra 2 from high school and you haven't used logarithms since then.
Well, don't you just raise dB over 20 to, or 10 to the power of dB over 20?
Yes. I'm getting there. Okay. Some of you remember that better than others. There probably about half the class doesn't remember that one. Okay. Inverse function of log is 10. So if I take 10 to the dB over 20, 10 to the log of something cancels each other out. It's an inverse function, and that just becomes AV. You can do that with natural logarithms too, but it works with any logarithm. If that was a ln, then you would just raise it to the e power. Okay. So 20 dB is just 10 volts per volts. So I use that value and I can calculate R2, 200 K ohm. And then I've got the transfer function and it looks like this. The only thing I change is I change the radians per second to kiloradians per second. Okay. I don't recommend doing this if you're around analog engineers, but this is one way to build a bandpass filter. You can build it all with one op-amp. But I got this, I copied this out of the book, I'm sorry. It's to give you an idea of how to do this. What I could do is I could take a low pass filter and I could follow that by a high pass filter, and then I could follow it by a stage with gain. And you'll learn how to get that all in one stage in 490, but it gives you a general idea of how you can do this. So you have this high pass filter to filter out the 1 over F noise that's really high in your electronics, and to filter out whatever the ghosts are, what noise the ghosts are making. I'm sorry, I can't resist that anymore. You have a low pass filter to filter out the high frequency components, and you have gain in the middle. And you can do that by setting like your high pass filter, your I don't think that's right, but you can put those together, and that's kind of a silly way of building a bandpass filter. Okay, but it can be done by just cascading stages. Remember, in the frequency domain, the beautiful part about the frequency domain, if I have one function and I pass it to another function, I'm just multiplying those functions together in the S domain. If you try doing that in the time domain, you get this horrible thing called the convolution integral. Don't do it. You'll get that in 348. We'll see who's teaching 348 and whether they have a sense of humor when you get in there. So we want to go back to these general circuits in the S domain, and this may be enough to help you get started. Well, you got the last problem on the homework. I think there's 3 problems on there. That's kind of a warning that they're all circuits problems. We're going to start looking at some of these techniques, and we'll cover this more on Wednesday. But we're going to look at that one pesky circuit that we finally figured out how to do something about. I told you the method. This was a couple of slides ago. The first thing you want to do is draw the, do I have the picture of this on here? That would be an amazing thing to do. Yes, I do. We're going to go to bamboo paper where I don't draw so much like a child. Oh, that's right. Okay, well, we'll write over some stuff. My notebook's full. And I haven't used it since then, so you can see I was scribbling whatchamacallit, that's 490 stuff. Oh, I want to go back. I got to do this. I'm getting a couple of pieces of paper. That one's almost empty. Oh, that one's Bodie Bloods. Erase. I want a white eraser. Does that do? Oh no, that's just blot. That's a highlighter. Eraser. Okay, so we didn't do that one. We're gonna go back to ink. Okay. So I've got the circuit. I had 10 e to the minus t u of t. We know, oh great. Let's go back to this. We know we can ignore the u of t part, and it was a voltage source. So this is 10 over s plus 1. That's 10 e to the minus t. I have a resistor, 10 ohms. I have another 10 ohm resistor, 10. I had a capacitor that was 0.1 farad. So 1 over SC is going to be 1 over 0.1 is 10 over S. Now, they said that there was an initial condition across the capacitor. My V of 0 was 5 volts. So I go back to that model instead of trying to derive it again. And if V of 0 is 5 volts, this comes up with my model. This looks like a parallel circuit on this one, so I'm going to make it parallel. It's a current source, and it has a value of C times V of 0. So in this case, my C was 0.1, my V of 0 was 5, so this is 0.5 amps. My delta of t function over there, I take the Laplace transform of it. The Laplace transform of delta of t is just 1. So this becomes, since that was 2 delta of t, that becomes 2. I'm still going to write the node voltage equations. This will be the last problem I do today. I don't have to write one here, because if I pick my ground node down here, I know the voltage at this point. It's 10 over S plus 1. So don't write an extra equation. This is going to be my VA. I have to assign current directions. So this is current, as I'll say, it's going this way, it's going down, and these are obviously going up. Now I need voltage polarities. I assign those based on passive sign convention. So current goes into the positive terminal. And as long as I do that, it will keep me from making sign errors. And I don't worry about those. So I write the KCL equation. I've got a whole section in my 188 review notes on node voltage method. It's my favorite method because back when I was first teaching 188 and I couldn't remember how to solve some of the circuits in the class, I could always do it by node voltage method. And the other professor, Dr. Brower, would laugh at me occasionally and go, "Oh, Julie, there's a shortcut." Well, yeah, but my answer's right. Yeah, yours took 2 pages. The shortcut took. Okay. You don't use this a lot when you're a working engineer, so I'm sorry. But it's good to know how to do this. No, that means I've got to go watch a movie in a half an hour. So going into VA, the ones pointing towards VA, I've got through the 10 ohm resistor, I've got 10 over S plus 1 minus the voltage on the other side, which is VA, and all that is over 10. Also going into the node, I have this one here, plus 0.5, plus 2, and then coming out, I have, it's VA minus 0, because this is going to ground. So VA over 10 plus VA over 10 over S. A very messy algebraic equation. First thing I want to do is just start changing it a little bit. I want my, okay, I've already moved to the left. Okay, now move back over to the right. This one I can clean up. Since it's a fraction divided by a fraction, I can get this S go away and just move it into the denominator. And then I'm going to multiply the entire equation by 10. This is why I hate teaching 188, by the way. 10 over, because it's too much algebra, S plus 1 minus VA plus 2.5. And I multiplied the whole thing by 10. I get VA plus, oh, VA times 1 plus S. I shouldn't have done that. We're going to move the VA over to the other side. 10 over S plus 1 plus 2.5 equals, okay, so I add VA, I get VA times 2 plus S. Okay.
Did you forget to multiply 2 by 10?
Probably. Yes, this side should have gotten multiplied by 10 too. Oh, and this should have gotten multiplied by 10. So that becomes 25. You're right. I haven't done this for a while. Now we're going to multiply the whole equation by S plus 1. And I get 10 plus 25S plus 25. Catch me on my algebra. Equals VA times 20 plus 10S I divide by 20 plus 10s, and I collect like terms. And that equals VA. So this would be 25 plus 10 would give me, I'm gonna change colors again. Oh, great, everybody gonna move to left. Let's change it to something ugly green. This becomes 35. So my VA is 25s plus 35, plus 35 over 10s plus 20. We're going to do some factoring. I'm going to factor a 25 out of the numerator. Sorry about this. 25 times s plus 35 over 25 is 7/5, which is 1.6 over 10 times s plus 2. We could put that into the standard form and make a Bode plot. We could do an inverse Laplace transform of it. There's all this math is related and applies to circuits. Did I get that right? By some miracle, did I get that right? Oh, I forgot to multiply that by s plus, I forgot to, I see what I did. So this would be times s plus 1, that term right there. And so then I would get s plus 1. We could take that and do a partial fraction expansion on it without factoring it. Yeah, that's fine. Once we do the partial fraction expansion, this is the only place I have blank paper. No, I just want to drag you. Come on, everybody move over that way. Okay. So let's just change colors. So we could do a partial fraction expansion on this. And we know this would equal some factor A over s plus 1 plus some factor B over s plus 2. We could use residues, and I don't want to do this, but we could use, it's getting long already. We could use residues to find A and B. And it's going to turn out that, and the details of all this is in the slide solutions too. A's 10 and B is 15, and we went over this recently. So then we take to find A and B. Then our next step would be to take the inverse Laplace transform. And we have 10 over s plus 1. So my V of t, my VA of t, I think is what I've been calling it, 10 e to the minus t plus 15 e to the minus 2t, all times my extraneous u of t, to remind myself that in taking the Laplace transform and taking the inverse Laplace transform, I've lost all information about anything that happened before t equals 0. At this point, when we had the function in this form, we could have drawn a Bode plot and found the frequency response. And you'd have to put it in standard form. So there's a lot of information gained doing this method and going into the frequency domain. And it simplifies the circuit analysis a good bit. This is probably where I should stop. and get a new bamboo paper notebook. Oh, wow. Is that that's just my internet frozen. I don't know if you saw that or not. I'm going to take roll, and then I'm going to send myself a text to remind myself to do the bamboo paper thing whenever I get like 3 minutes. So there was a point to all that math. And we've learned a lot of techniques. If you go to work for General Dynamics, they build military radios, custom military radios. They do a lot of this stuff because when you're building a radio, it's all about frequency response. Raytheon down in Tucson also hires a lot of our engineers, mostly as test engineers, but they do missile, but it's RF circuit analysis. So there's a lot of this frequency response work there. Also places like, what's the place called? Viasat is what it's called now. All the former Motorola's that had nothing to do with semiconductors that are now just have different names on them down in the valley. They do, there's a lot of satellite work down there. There's a lot of RF work down there. There's also a lot of semiconductor work in Arizona, and most of the electronics divides in those two with some power people. But power people, never mind. Power people can get hired anywhere. Let me take roll. Mubarak.
Yes, I'm here.
Yay. Nicholas Arnold.
I'm here.
Okay. Zach Price.
Here.
Doherty. Tyler Shepard. Taylor Twitchell.
I'm here.
Okay, is I'm Taylor?
Yeah.
Okay. Yeah. Fabian. Okay, so the only people I have missing today are Tyler Shepard and Fabian.
Oh, wait.
Oh, and you're here. So Tyler Shepard. Okay, have fun. We got an extra, wait, what?
Not Tyler.
You're Tyler Shepard, okay.
No, I'm Fabian.
You're Fabian, I got you, Fabian. Okay. And if I ever mess up on the roll, just send me an email and I'll fix it. I won't argue with you. Okay. IEEE movie at 5:30. And then we'll do a resume workshop or something. We'll figure something out to do. Okay, stop share. And everybody's leaving. And